Hello, my name is Levi Starrett, and today I will be showing you some of the work that we've been doing with interdomain messaging using MASL and Kafka. Before we get into the presentation, I want to give a quick overview of the roadmap. First, I'm going to explain the problem that we intend to solve. Then my colleague Tristan will give some context to the MASL C++ architecture and code generator. Finally, I will show how we've solved this with Kafka and give a quick demo. My main goal for this presentation is to give a good example of separation of architectural and application concerns using code generation. And secondary goal is to highlight the MASL C++ architecture and model compiler. This is a free and open source software architecture and model compiler that has seen some serious improvements in the last 6 months. So if you're interested in that, keep paying attention. First, we have to have a problem. As you've already heard in the protocol verification presentation, we have this application that takes input as audit events and processes them according to a set of job definitions. I've simplified this system to 3 domains for this presentation: reception, ordering, and sequence verification. In the very simple deployment, this application is deployed as a single process with all of the domains in the same process, and messages between the domains being implemented as simple C++ calls. But this isn't good enough. We need to be able to scale horizontally. So first, we want to separate the reception domain into its own process and keep the ordering and sequence verification domains in a separate process. We need to be able to communicate between these 2 processes. In addition, we need to be able to dynamically scale these to multiple instances of all the domains with their own independent instance populations. What we need is some sort of bus type of message delivery system that allows these domains to communicate with one another. This system needs to be able to work for both internal messages, so messages between the domains in the modeled system, as well as external messages, such as data coming from the outside world and different types of systems. So as stated, our solution needs to be able to support both types of messaging, internal and external. We want to have flexibility of deployment, so we want to be able to deploy as a single process or as the fully distributed and scaled system. We want to be able to have the architectural and application concerns separated so that we don't have any pollution of architectural mechanisms in the application models themselves. And we want to have no impact on the application models themselves. In other words, we want our modelers to be able to model and our architects to be able to build the architecture with no pollution in between. We chose Kafka as our messaging broker service solution for a variety of reasons. It fits our architectural profile and allows us to satisfy these requirements. It's well supported by the industry, as well as having an existing base of expertise, which allows us to be able to support this application long term. And now Tristan is going to come on and give some context about the MASL C++ software architecture and code generator.
Thanks, Levi. Let's start with a quick introduction to the MASL C++ architecture. It builds and runs on any Linux platform and uses real-time signals for timers and process coordination, which unfortunately means that it doesn't build and run on Mac or Windows at present. It's single-threaded in the main application, although peripheral libraries can run in separate threads. All application-level processing, e.g. state actions and services, is done in a single thread even across domains. A plugin system is used to allow configuration of features and capabilities. Some of that configuration is decided at compile or link time, and some can be altered at runtime. One of the compile time decisions is persistence, and by default each application will be built with both an in-memory transient version and a version where the instance populations and timer events are persisted by an SQLite database. Inter-process communication is also compile time pluggable, and we'll explore the mechanism for that in a moment. The code generator is written in Java. It's using Antler to parse the static models and action language, and it's open sourced in the xtUML area in GitHub. When each domain is built, it produces a number of libraries that can later be linked together in various configurations to form an application. The interface library contains definitions for public types, service signatures, public domain services, along with mechanisms to register implementations for those services. The core library contains implementations for domain services, state machines, state actions, class and instance services, and a mechanism to register implementations for terminator services, with a default, usually empty, implementation provided by the domain. It also provides base classes for handling instance populations, mechanisms to register a full implementation. When this core library is loaded, it registers its domain service implementations with the application via the interface library. The persistence libraries provide full implementations for handling the instance populations, and currently, as I said earlier, we produce ones for in-memory transient populations and one for SQLite persistent populations. The code generator also produces a number of supplementary libraries that can be loaded at runtime by the application, depending on which plugins are active. For example, the inspector, which allows model-level debugging of a running process. That'll load libraries containing metadata describing each domain and hooks to evoke services and generate events, that sort of thing. When we build domains together in an application, we decide which domains are included in the same process by either loading only the interface library or by loading the interface and the core library. If the core library is loaded, it registers its domain services with the interface, and they'll be called whenever the service is invoked from the interface. If only the interface library is loaded for a domain, as we see here for domain C, another mechanism to handle calls must have been registered. Typically that mechanism will send out a message to the IPC to another process ready to receive the calls. The way we do that is that the IPC code generator adds the calls into the interface library and then registers the IPC calls as the default to be used when the core library is not loaded. But we could do it by just including another IPC library for each domain, which does the registration. The packaging configuration in terms of which domains are co-located in a process and which are distributed in separate processes is determined by the PRJ file, which we'll look at in a second. Then utility domains are loaded at runtime depending on which command line parameters are specified at startup. So in this case, the inspector utility has been specified with -utilinspector, and the main inspector's library is loaded dynamically at startup. And in turn, this loads the libraries it needs for the domains or interfaces included in the process. So a domain in isolation has no knowledge of any other domains, so the information or messages it can receive are defined by its domain services, and the message or information that it can publish are defined by its terminator services. So those are its two interfaces to the outside world. It means we don't have any inter-domain pollution of subject matter concerns. So in this example, we've got the domain providing the accept events service to the outside world, and that allows it to receive messages that will cause that service to be invoked. And it's also, if it calls its ordering.acceptEvent terminator, that will publish that information to anyone else that's interested. But how does it know who is interested? Well, inside the .prj file, we have the project definition defines which domains should be co-located in a single process, and the terminator service definitions are overridden to make calls to one or more domain services on other domains. So as you call the terminator service, that's overridden, and that will have calls to a domain, but that's all defined at the project level, so we don't get the pollution in the domains. And that definition handles any impedance mismatch between the terminator service signature and the domain services it's calling, for example, type and unit conversions, or maybe if it might be a fan out, so you're sending the information to more than one domain. So calling the terminator service then calls the domain service handler to be invoked with the correct parameters. If both the source and destination domains are co-located in the same process, that handler will have an implementation from the core library registered, as we saw earlier, and that will be invoked directly. But if they're distributed on the network, the handler will invoke the IPC mechanism to send the message out over the network. The mechanism by which a domain notifies the network that it wishes to receive the messages corresponding to its domain services is implementation defined, but might typically involve tagging the service with a topic to subscribe to at startup, or having a utility domain that can handle the dynamic registrations. And now I'll hand back to Levi to explain how the Kafka implementation handles all of this.
Thanks, Tristan. Now, with that as a backdrop, I want to get into how our implementation actually works. So you can break down our Kafka implementation into 4 components. The first is the Kafka utility library. This is the part of the system that's common to the entire deployed system, including all of the domains. This handles connecting to the messaging broker as well as registering topics and processing incoming messages and publishing outgoing messages. The second component is the topic registration component. So this part is generated for each domain independently and makes a connection between registering topics and the actual domain services that need to be registered. So for each marked domain service, the code is generated to be able to actually register that as a topic in the system. The third component is the corresponding piece for publishing. So this is also code generated for each domain. For each public service that's marked as a Kafka topic, code is generated to pack up the parameters and publish that using an API call to the Kafka utility library. And finally, data marshalling, which is really just a subcomponent of the Kafka utility library. This is the part that takes all of the modeled data types and parameter types that we're using and packs them into a data format that can be sent across the Kafka messaging broker. And we borrowed this directly from the existing data marshalling binary format that's used by the process inspector. So calling back to the diagram that Tristan showed you, now we have a process that starts up, and the main process starts up just like normal. Then when the Kafka utility library starts up, it connects to the messaging broker and creates an instance of the consumer class. Then when the domain-specific libraries load, the topic registration piece gets activated, and each of the domains register their public service as subscriptions on the Kafka consumer. You'll notice that in this example, domain C is an interface library only. This means that instead of the topic registration piece, it includes the publishing piece. So when domain A and domain B want to make a call to a domain C public service that's marked as a Kafka topic, it will package up those parameters and publish it as a message to the Kafka broker. Here's a little snippet from the AE ordering domain mod file. You can see that we have a public service called xtEvent, and it's marked with the Kafka topic pragma, which allows the code generator to know that it needs to generate publish code and topic registration code for this service. Here's a snippet from the topic registration code for AE ordering. For the xtEvent service, the message data is passed in as a stream from the Kafka utility library as it's received from the Kafka messaging broker. It's unpacked into instance fields, and then the domain service is called with the message data attached. On the other side, we have publish code, and in this case, when the service itself is called, the parameters are packed into a messaging buffer and passed to the Kafka utility library for publishing. Okay, now I want to show you a demo of this in action. So I have the protocol verifier running here with 4 instances of reception and 4 instances of AE ordering and sequence verification. And I'm going to use the plus to JSON utility to start generating events, and I'm generating 1,000 events at a rate of 500 events per second. So you can see the application is processing this information. The events first get published to the reception domain in its own process, where it's validated and unpacked from its JSON format, and then passed to the AE ordering. So it's completed, and you can see all of the job success messages. Now in our Kafka Explorer here, we can look at the reception topic, and each of these messages is a JSON event. And you can see it's in just JSON format there, and we have all of these messages that came in during the run. They get processed and then republished to the ordering domain. It's a little bit more compact. In the consumer group, we can see we have 4 reception instances, and each of these reception instances is assigned a particular partition of the reception topic. So 0 through 3, they're assigned, and you can see that each instance handles about 1/4 of the load. We do have ongoing work in this area, so here are some future enhancements that are planned. I'm not going to go through all of them in depth in this presentation, but if you'd like to know more information, or again, if you would like to understand how you can run an example model using the MASL architecture, please let me know. My email is there on the screen. You can also come to the xtUML community chat on Google Chat. And with that, I'll ask for questions. Thank you.